So let's begin. Sorry. Let everybody settle down. So let's begin. About 8 to 10 months back, our team had an idea about a few algorithms that could be used to make the process of analyzing corporate and business data quite efficient. So the problem that lay before us was we needed a very versatile framework to test these algorithms. The framework that we needed had to support real time. So we had very few options at that time in the market. And the data that we targeted was basically graph data, that kind of data which had a lot of relationship between them. So after months of searching here and there, we finally found our desired framework. And the two most important parts of this framework was Storm, which took care of the distributed and real-time processing, and Neo4j, which is a graph database, and it took care of the data storage. So what are the problems that we faced? The corporations today and basically online businesses, they generate huge amounts of data. This data multiplies exponentially each day, and the major problem is storing this data and retrieving it back in an efficient manner for analysis. Moreover, it's not just storing the data. What these corporates require is analysis of this data in order to gain some useful information. And that is also a very big challenge for them. Another thing is social networks are growing everywhere. You can say that every college itself has a social network nowadays. Kids in first year start building their own social networks. So with popularizing social networks each day, the amount of social data is also growing. And there are a lot of applications of this social data. Personality profiling is one of them. And there are a lot of projects that go on about personality profiling with use of data from Facebook or Twitter and information that people put up about themselves. Another thing is business intelligence. Business intelligence is used for mainly online marketing. It's not that it's only online marketing, but at present, mainly the online marketing scenario uses business intelligence tools to decide what kind of products attracts more customers. And as we had a talk yesterday, we saw that what are the challenges of online marketing. So how to attract more customers. But that was the front end. What happens at the back end is how the company itself knows that what kind of products and what kind of offers to bring out to attract more customers. So we'll see how that helps in business intelligence. And there were a lot of constraints in real-time and fault-tolerant processing due to lack of documentations mainly, lack of knowledge which is open source. So what I'm going to talk about in this talk is, we'll take a look at the Storm as a distributed computation framework. We'll see NoSQL database, Neo4j. We'll see some really cool pictures. And finally, we'll get to what we are trying to achieve through this framework. Now, Storm and Neo4j are in themselves very large topics. So this is kind of two workshops combined in half an hour. So I'll just present an overview of Storm and Neo4j to get you more interested in them. And we'll have less dirty details. And I'm going to go pretty fast, so please bear with me. First, the first part, we look at Storm. And many developers have called Storm as the Hadoop of real-time processing. So in a way it's correct, but Hadoop has been in the market for a long time, much longer than when Storm came into the picture. So why to switch over from Hadoop to Storm? So we do have Hadoop, but what is common between these two frameworks is both are distributed processing frameworks, both are fault tolerant. Hadoop in itself processes large but finite jobs. So when you submit a job, you have to define the beginning and the end. So you know what is the limit of the data that is being processed by the Hadoop cluster. Moreover, it processes a lot of data at once. And finally, Hadoop has high latency. Whereas when you switch to Storm, you get the flexibility of infinite computations, which in Storm we called topologies. They process infinite streams of data. So stream processing comes into the picture. And the data is sent in the form of tuples. The streams actually consist of tuples. And Storm, on the other hand, has low latency. So overall, what Storm gives us is, it gives us real-time computations. You can guarantee that the data you're passing to Storm to process will be processed. There's a process of acknowledgements, which Storm ensures that if a data tuple is received by the next node in the cluster, it will get back an acknowledgement. If it doesn't, it will resend the tuple. So we'll see the details of how it does that. There is horizontal scalability, which is the biggest factor. So if suppose there's a company like Flipkart, which has increasing customers day by day. So what happens when you see that your customers are increasing exponentially? You try to increase the performance of your systems, and that is vertical scalability, which has been going on for a long time. And horizontal scalability, on the other hand, deals with increasing the number of nodes in the cluster, increasing the number of machines that perform the task. So Storm in itself is very flexible. When you add a node to a Storm topology, all you have to do is reconfigure your topology. It's just a single command, as simple as that. And finally, there's higher abstraction. I'm sorry, I missed message brokers. So another advantage that most developers hate about distributed systems is message brokers. So Storm does away with the message brokers. Actually, you don't get into the details of message broking. Whatever happens on the backend. To the user, it is very highly abstracted. And so all you have to do is concentrate on what your work is. You don't need to worry about how Storm does it. Let's go a little deeper. We'll see what are the components that make up Storm. First thing, we have spouts. We have streams. Streams actually is an unbounded sequence of tuples. So one question that a small definition may arise in your mind is, what kind of a tuple is this? So a Storm tuple is nothing but the closest thing that you'll find to a Python tuple. When you pass data to a Storm topology, the tuple that is going into the topology can be made up of multiple types of data, multiple forms of data. It can have text, it can have images, it can have music, anything. So it's quite flexible. You can pass a single data, you can pass multiple data items in a single tuple. So we'll see how Python helps us to deal with these tuples, and although Storm is written in Java, let me tell you, but Python gives us that flexibility because it has some core features which matches the features of Storm. So as much as the developers of Storm did in Python, did in Java, it's much easier for us and happens in less code when we try to pass a tuple to a Storm topology. Next we have spouts. Now spouts are those components of the topology which produce the streams. A spout has basically it has the code which takes in raw data from a source. And one question that you might ask is, what is the source for the spouts? Where does it take the data from to produce a stream? The answer to this is Storm can take raw data from anywhere. If you have an API, a streaming API like that of Twitter or any other streaming API, you can just include the functions of this, the API into Storm spout. It will take the data from that API, convert it into a continuous stream and pass it on to the topology. Next, you can input raw data from a database. So no matter what kind of database you have, just use an adapter for that database wrapper, and you can give the spouts raw data. And lastly, you can use simple text files. That is the best for testing, in fact, on a single system. So the next is bolts. Bolts are that part of the topology which process the data, which do the actual processing. You can say these are the neurons if you consider a storm topology as the brain. So what happens is all the code that you need to work on the data are included in a single function called process, and this function is called continuously in a bolt. So as you can see in this picture, I have shown that there are two input streams that are coming into it and one output stream. But is it necessary? Of course not. It is so flexible. You can have as many number of input streams and as many number of output streams. So a small example that I'm giving you, suppose your input stream consists of sentences, and you process it in the process function by splitting the sentence into words. You create streams out of the nth word and send them out. So the first word goes into stream 1, second word goes into stream 2, like that till stream n you can send your words. So it is taking in one tuple as an input, and it is sending out multiple tuples in multiple streams. What we have next is topologies. I've been talking about this from the beginning, so now we'll see what a topology is. It is basically a network of spouts and bolts. How you arrange the spouts and bolts according to your requirement in order to produce a full-fledged working cluster. That is what a topology means. So is that it? No, it does sound simple, but there are more to it. To increase the power of this topology, we introduce parallelism, and parallelism is implemented in Storm with the help of tasks. Now, what are tasks? Now when you deploy a spout or a bolt on a cluster, a single spout or bolt can have multiple instances of itself running on multiple nodes of this cluster. So that suppose you have like the word bolt I mentioned before, there are multiple sentences that are coming out of the spout. When they reach a bolt, you have a single bolt to process it. But what if that bolt replicated itself into multiple instances of itself? So you can send one sentence to each and parallelize the processing. So at a time you can process n sentences. So this gives an added advantage to Storm. Okay, so a basic question: when a storm comes out of, when a spout emits a tuple, where does the tuple go? I just mentioned you have n instances of a single bolt. So how does the tuple know which instance of the bolt it is going to go to? So Storm provides something called groupings to the rescue of Mr. Tuple. The four basic groupings that are used: first is shuffle grouping, where the tuple that is emitted goes to randomly any one of the existing tasks. So this is the most widely used because in a way it guarantees that on an average a single bolt, the number of tuples will be distributed equally among all the bolts. So on a probabilistic factor, this is preferred. Next we have fields grouping. This is when your requirements are much higher. So you perform a mod hashing on a subset of the tuple fields. What actually happens is you define the tuple, like let me give it by an example. So the sentence that you're emitting contains words and numbers. So if you want numbers to go to one particular, bolt, set of bolts, and you want words to go to another particular set of bolts. So you label the tuples as numbers or words, and based on this field of number or word, the tuple will be sent to either the number bolts or the word bolts. So this is based on field. Next is all grouping. This is it's a sarcastic kind of grouping. I don't know why they introduced it, but it sends the tuple, it creates clones of the tuple and sends the clones to each of the bolts that are existing in the system. So probably nobody will miss it. And last is global grouping, in that the tasks that are running have IDs. So it picks the task with the lowest task ID, and it sends the tuple to it. So when it receives a tuple, it increases its ID, and the next one that is lowest will get the next tuple. There are other groupings which are called none groupings, so you can check it out in the documentation of Storm. But these are the four that are generally used. So what does the Storm cluster look like? These are the components that we discussed. Now how to deploy them on the cluster? So in a cluster, you have multiple nodes. So the master node of the system is called the Nimbus. It runs a daemon on it, which is called Nimbus. The function of the Nimbus is to control all other nodes of the system, as well as to control itself. On the other side, you see supervisors. Supervisor is a daemon that is running on the tasks. Each other node, which is not a Nimbus, contains a daemon which is called supervisor. What is the task of these daemons? They help to coordinate the input tuples, the output tuples. It helps to coordinate failures. It helps to restart the bolt in case it goes down sometimes. So if this was Hadoop, Nimbus was called the job tracker, and the other tasks will be called the task tracker. But this is not Hadoop. So the nodes in a Storm topology are stateless. They don't store any data. They don't store any information. They receive, process, pass out. So in case you want to coordinate between them, how do you store data and how do you coordinate between them? That is why a layer of Apache Zookeeper cluster is present between the Nimbus and the supervisors. So the function of the Zookeeper is to coordinate these stateless nodes who cannot think basically. They're just doing what you tell them to do. So the thinking part and the memory part is for the Zookeeper cluster. So you get it, the basic function is to coordinate everything. So if you talk about the salient features of Storm, we said that Hadoop does batch processing. Storm, on the other hand, does stream processing. So what if you wanted batches of data to be processed in a stream? So the versions of Storm greater than 0.7, they support something called transactional topologies. Transactional topologies are basically group your input into small batches. And if failure occurs during a commit, suppose you want to commit to a database, and if failure occurs during a commit after processing, the entire processing of that batch is redone as well as the commit process. And suppose before commit, while processing you encounter an error, so the further processing is stopped and the entire batch is processed again. It is a little less in performance if you think compared to Hadoop, but on the other hand, it guarantees message processing. It gives you the full the confidence that your data tuples will not be missed. Next is by using acknowledgements. I already mentioned this, so we'll see that in the program. So what are we using in Python to write Storm topologies? There's a package called Petrel, which is written by AirSage. It's a Python wrapper for Storm. You can write and submit topologies in Python. So let me tell you why I went for Petrel. Initially, the Storm package that you will download, that has support for many languages. But you cannot define topologies and submit topologies in other languages. It just allows you to script the bolts and the spouts in Python. So in order to do the whole thing in Python, you needed a better wrapper. What Petrel does is, it gives you the flexibility to write even your topology in Python, to submit the topology to the cluster in Python, debug in Python, sort of everything in Python. But it's still a developing package. It's relatively new, it's a couple of years old. And last year in PyCon US, Gabriel Grant gave a talk on Storm in which he talked about a package called Umbrella, which would be used as a Python wrapper, but I don't think it's released yet. So for the moment, we would have to do our work in Petrel. So let's quickly take a look at Neo4j, and then we'll come to the demo. So when you have graph data, graphical data, which is sort of represented as nodes and relationship between nodes, and you want to fetch something out of a database, relational an RDBMS that has such graphical data stored, it's actually maddening for a programmer to do hundreds of joins in order to get just a single piece of data. So this is actually how data was represented in RDBMS, but relational data required something more and something more pleasure to work on. So enter NoSQL databases. So we'll take a look at the type of NoSQL databases. We basically have 4 types: key value stores, column family, document databases, and graph databases. And their names pretty much explain what kind of data and how do they store it. So what this graph demonstrates is the type of data and the quantity of data that a NoSQL database can handle. We see that a key value store can handle a very large quantity of data, but the complexity of data that you can store in a key value store is very low. I mean, it's obvious. It's just a key and a value that you're storing. You can't store a very complex data in that. On the other hand, a graph database, it is a sort of a WYSIWYG database, you can say. Whatever you think, you can put it on a graph database as it is. So it can handle data of very high complexity, but since it is it's basically a disk database, it is dealing with a low amount of data compared to a key value store. So you have to sacrifice either complexity or data size in order to get an edge over the other. So let's see why we should prefer NoSQL databases. First thing is scalability. So when we are dealing with enterprise applications, business analytics, we have to keep in mind scalability. So the biggest advantage that they give us is they are easily horizontally scalable. So suppose you have a relation in RDBMS and you want to scale it. There are a lot of intermediate tools that you have to use in order to make a database existing on two machines, and even the consistency between them is a matter of doubt, because they're not that consistent if you spread the database across multiple machines. So a NoSQL database is easily horizontally scalable. It has dynamic schemas. It will handle unstructured data really well. So what happens is, if you've gone through data mining topics, you know that from an RDBMS, when you take data and you want to process it, and if by chance there are empty values in that, what we do is we guess those values and we put them in that. We try to come up with the missing values, because if your values are missing, it may be that at some point you get null or none errors in the execution. So in order to do away with all these schemas, NoSQL databases came up with dynamic schemas. So as and when required, you introduce a field. It's not that you have to predefine that yes, these are the headers that under which our data will be structured. Your data, as and when it comes, you can store it. And suppose like you're saving a form data from a website onto a NoSQL database. If a user wants just his name to be given in the form, then just the name will be a field that will be present on that user's account. You will not have other fields occupying unnecessary memory spaces. If a user wants to enter his complete biography in that, well and good. All the fields will be defined for the other user. So as and when required, the fields are defined to store data in a NoSQL database. And of course, they do excel in speed and time, but this is an important point. There's a trade-off in consistency for efficiency. You sure don't want that. But there are scenarios where this is a very useful factor. NoSQL databases, why I am talking it is in the sense of business intelligence. So if you have a huge customer data from a xyzcart.com and you want to analyze that, and you say that the graph database is inconsistent, that means either we are missing out on a few values or it is dropping a few tuples here and there. But will that affect you much? You'll still get 99.9% of the exact result that you wanted to get. So in such cases, we can get the efficiency at a cost of a little consistency. So where do we not use these? NoSQL databases we shouldn't use in online transactions where money is involved. Like suppose if PayPal uses such databases, it will get bankrupt in say 2 years. So that is the scenarios where you avoid a NoSQL databases. But graph databases are those NoSQL databases which are completely ACID. They are consistent, and we'll see why. Next, they are a pleasure to code. The language is not a limit, and you can use any query language for it, even SQL. I know most people in our development team, when we introduced them to NoSQL databases, they thought NoSQL means no SQL. Okay, so the actual thing, yeah, that's true. Many people still don't know what it is. So NoSQL actually meant not only SQL. It just defined the flexibility in the query languages that it gave. So you can use even SQL if you are comfortable with it. And the last thing is, there is no downtime. So suppose you have a website which is running on with a MySQL server, and you want to put it down for maintenance. So you have to display an ugly message on your website. Sorry, we'll come back in 2 hours. We are down for maintenance. But think for the other hand, if you have NoSQL databases, which are highly distributed, you have millions of nodes running, and each of them saves a part of the data. So what you can do is you can maintain one node at a time. And for that, for the users querying that node, they'll probably think that the internet connection is slow. That's why they didn't get the page. Whereas all other users will be able to access it. So if your friend is sitting beside you, he's able to access, and you are not able to access, definitely they're using a NoSQL database at the end. And they don't need to have downtimes. So the property graph model of graph databases has 3 main parts. We have nodes, we have relationships, and we have properties. So an entity is stored in the database as a node, and you can save anything about that entity as properties of that node. And how 2 entities are related is measured by relationship. You can define the type of relationship and any other properties that you can think of for that relationship. Since it is a disk database, it stores all this information in an unstructured fashion. So as and when required, it can be retrieved. There are traversal frameworks because if you want to go from access one node from the other node, they have defined highly efficient traversal frameworks. So you can perform queries on these connected data sets. We have bindings for REST, we have bindings for Gremlin, and we have bindings even for HTTP. So Neo4j basically is a fully ACID. It has rollback support. Yeah, that's unbelievable. So because I told you that NoSQL databases have less consistency. Next is they are schemaless, and efficient storage of semi-structured data is their main property. They have fast, deep traversal instead of slow SQL queries. So like in case of Neo4j, the query language that is used is called Cypher. It is, it's really an awesome language. You can find relationship between nodes just with the help of arrows. I mean, how cool is that? You can say A to B. You can find a relationship between A and B. You don't need to write those capital queries in SQL. Biggest thing is it is whiteboard friendly. So in an office environment where a lot of ideas come from a lot of people and you jot down those ideas, but when you go to implement them, different people have different perspectives of writing the code. So when you have a whiteboard friendly technology, it helps to unify your code, it helps to maintain consistency within the organization, and you get better productivity. Next is they are very natural to express graph related problems with traversals. So if you have a shortest path problem, which is in fact it is the biggest used problem for graph databases. So if you have a shortest path problem, then graph databases is your nectar. Then how do we Pythonize Neo4j? Unfortunately, this is also written in Java. So Py2Neo is a wrapper, which is an excellent binding for Neo4j. Nigel Small is the contributor of Py2Neo, and it's an open source project. It is also a developing project like Petrel. So some functionalities like labels are yet to be included, but since it is open source, well and good. Even we are working on it, and I hope people here will also work on it. So we're definitely going to have a good Python wrapper for both Storm and Neo4j in the coming years. So will relational databases be extinct? That's a big question. But thinking about it, for a few decades to come, I think that relational databases are still a way to go, have still a way to go. Because the data that we have and the type of functionality that we implement on the data are both different for different organizations. So a DBA or a system admin has to analyze this data well. If it is a banking organization or an online transaction company, then relational databases are the thing for you. You should never look at inconsistent databases for that. Whereas for people like us who are more into business intelligence and data analytics, we can do away with a little consistency because we need performance. And that is what NoSQL databases and graph databases give us. Okay, seems to be. Okay, let's get into a little coding. The demo that I'll present here is based on some sample social network data set. Okay, I think I missed a slide before. Yeah, categories of graphical data. So presently you'll get graphical data from social networks, from citations. You'll get product co-purchasing from torrents or any other peer-to-peer networks. You'll have mapping data and road networks. You'll have web graphs, and for matter of fact, you can also have weather data. So there's an excellent source of graphical data if you want to catch hold of some sample data to work on. This is a site which I found of Stanford, which gives you really good data sets. So I'll be using one portion of this data, which I got from this site. So this social network data set, it includes data about people signing up on the website, detailed information entered by the people, adding friends, unfriending, and this is based for 1 month of activity. So Neo4j will be used to store and update the social data, and we'll calculate something which is called friendship index. Well, you might have used this thing, you might have known this thing, but this is a term which you might not have heard. So what exactly is friendship index? Through how many people a person A is connected to a person B. That's what we call a friendship index. So suppose I am friend with John, and he's a direct friend of mine. So the friendship index for me will be 100%. But if John is a friend of Scully, and I find what is the friendship index between me and Scully. So it might be possible in real life that somewhere in a party or somewhere I might have met Scully and John might have introduced me to him. So the friendship index is 50%. The chances that I know Scully is 50%. So that goes on with millions and hundreds of nodes. So it gives an idea about how close two people are. And another thing is that you can have multiple links between one person and the next. So what we do is we find out the shortest path between the two people. And that is done beautifully using graph databases. And they are useful while finding friends on social networks. We have something like friends of friends concept in Facebook's graph search. So there's no doubt they might be using a graph database at the backend. So this is the topology that we came up with. We designed a toy API which will give data into a spout. The update spout will take update data, and it will continuously keep updating the graph database through an update bolt. We'll have a query spout where if somebody wants to find out the friendship index of him and some other person, that will be processed by the query bolt, and both will be accessing Neo4j through the RESTful API. So this is how the code is structured for a spout. The first line is logging, import logging. So why did I decide to have my own logging? Because the Storm itself has a very good logging system, but when we come to Petrel, the logging is yet not implemented. So we have to define our own custom logging. We import our sample social network API, which we designed just for a toy API. We first we define a class which updates the spout. We initialize the class, and we declare what type of output fields the tuple will be sent out into the network. So here datum is just signifying that we'll send one element in the tuple, which will be called datum. The next thing is in this place you have to define how you get the data, from where you get the data. So in this example, I have taken the data from our toy API, whereas you can take it from a file name, you can take it from database, or anywhere you feel like. The most important method here is next tuple. This is the only method that continuously gets executed. You don't have to call it. Storm automatically executes it continuously. This is the one that converts the raw data into a tuple and sends it in a stream. So it is as simple as this, just two methods, and you define a spout. Storm.emit here is a function which is provided by the Petrel wrapper. It helps you to structure a stream and provide it with a time interval and send it in a stream. So that's it for a spout. So this defines what kind of tuples are being emitted, and this gets and emits the tuple streams. Next you have an update bolt. Here it's almost the same thing, just we have a difference in the methods. Instead of the next tuple method, in a bolt you have the process method, and all your code regarding how you get that, how you get the data from the database, how you send it to the database, how you write back, everything is mentioned in the process method. So in this line, if you see, we initialize the graph database to, since it is running on my local host, you can put your server address there, through a Neo4j graph database service. We create a person index and a friends index. So what Neo4j does is it uses Leucine index at the end. Apache Leucine is a beautiful project, you should look into it. So in this indexing service, we create two indices. If it is created, we retrieve it, we hold the handles in person and friends. We use the handles to create nodes here. These nodes, if not existing, are created. If existing, just return the handle of the node. And what you see within the curly braces there, name colon n1, we define the properties of that node in a single statement. Similar thing is done with the relationships. We define the property node 1. We define what kind of relationship is there. I call it knows. You can define your personal relationship. So node 1 knows node 2. And another property of the relationship that I defined is from. From when do they know each other? So let's have a fixed, assume a fixed knowing time, that's 1990. And finally we emit the tuple. If it is successfully updated, we just emit a tuple. So this objects for database access and indexing service. The process, as you know, is the most important method here. Since we are running out of time, I'll just show you the demo. You can see the code in the presentation later. So it's on the same line. It just shows you the tuple to be emitted can contain multiple entities. So we have a query bolt on the similar lines. It retrieves caller friend and request friends IDs. So you can take a look at this code. I'll just run topology and show you. So this is how the Neo4j interface looks like. I have a sample graph which has this many nodes and properties and relationship. You can go to the data browser. The data browser can show you a visualization of the data. So here I see one and it's connected to 219 nodes. But what if I want to see the whole graph? I select all. And this is okay, so it's processing very slowly. So suppose I just select some nodes out of it. So you can see how they rearrange themselves. Okay, so if you click on that 233 nodes and select all, it will give you a complete graph of that. Since my machine is running quite slow now, I cannot show you that demo. But it gives you a superb feeling. Like the first time I did this, I felt that if I was Tony Stark and I had Jarvis with me, I could just open the whole database in front of me and view the nodes. That was a wonderful feeling. Just try that again if I can show you that. Yeah, it's something like this. So it will grow completely and show you each node by itself. If you just click on a node, it will show you how it is connected to all other nodes. So this is the database browser that you have. Another thing is the console. We have three types of consoles: the Neo4j shell, where you can submit cipher queries. You have the Gremlin shell, where you can give Gremlin queries. And last is we have the HTTP shell, where we can get REST information. So I'll just run one or two commands and show you that. So this node is existing. So I gave a node ID as 1, and it showed me all the information that is existing for node ID 1. Similarly, if you want to see the properties of this, you just type properties, and it gives you, it has a name of 0. If you want to do the same thing with relationships, just type relation. So it gives you the properties of a relationship whose ID is 1. So it has a f index of 1, it has from timing of 1990. So if you go through the documentation of Neo4j, there are a lot of commands which you can directly execute in a graph. So I feel the REST API is much simpler than a normal Java API, because it gives you a client server sort of feeling, and it's really simple to use. So this is the documentation, docs.neo4j.org, where you can find the commands, and this is the REST API documentation. And I'll run a Storm topology. So we have a script called build and run, and you have to submit --config for the configuration file to get loaded, and you have to submit the name of your topology in the form of a YAML file. So it takes its time, and it instantiates. Now one major problem you'll see here is you won't understand anything. That's because when it was implemented in Java, they had a feature to turn off the debugging mode. But when we run it in Petrel, unfortunately, I don't know why, but the developers of Petrel forgot to mention that how to turn off the debugging. So all this data that you're seeing is Storm debugging itself, and when you have to find the result you wanted, you have to scroll back, search each line, and find where it is. So that's something we are working on. Most probably it will be solved in a few months. So I'll just stop it manually. Since this is an infinite topology, it won't stop. It will go on until my machine runs out of memory. So I'll just stop it forcefully. I'll scroll back and I'll show you. So you can see here what kind of tuples each bolt is emitting, what kind of tuple each spout is emitting. So we see that the update bolt has given a spout of 7819. The query spout 151025. Some of these are actually names which we have hidden in form of numbers to since it's an actual social network data. So this is how it works overall. Okay, we are really out of time. So just three final thoughts. A Storm Neo4j framework is actually a boon for real-time graph computations. It's quite flexible. And as I mentioned, it's up to the admin or the developer to decide what kind of framework to use for their specific organizations. If you want to play with Storm and Neo4j, here are a few resources that I mentioned. My talk and the source code will be available on my website. And that's it. Thanks for listening. Okay, I'm open to questions if we have time.
Yeah, so we can take for like at least 2 to 3 questions.
Hi, Sonal.
Hi.
First of all, nice presentation.
Yeah, thanks.
I believe you mentioned.
I can get you.
Hello. Hello. Okay.
Yeah, speak a little louder.
Okay.
Yeah.
I believe you mentioned Storm is a fault-tolerant framework.
Yeah, right.
So if Nimbus fails down, or Zookeeper or Supervisor fails down,
yeah,
how will Storm
yeah.
be?
I forgot to mention that. Right.
Yeah.
So if your supervisor fails, the Nimbus that has the capability of restarting a supervisor node.
Okay.
So if it is unrecoverable, if it is recoverable, your Nimbus will restart the node. If it is unrecoverable, the task that is performed by that node will be given to some other node in the cluster. So there is no loss in performance.
Okay.
And as you asked, what about Nimbus? If Nimbus fails, then the Zookeeper has code which can restart the Nimbus. Because yeah, Zookeeper has code which can restart the Nimbus. Because Nimbus is the master node, it controls all other nodes, and no one controls it. Pardon? No, it's stateless. Right.
Hey. Hi.
Yeah. Hi.
Actually, you did mention that it may not be really a good idea to really use the NoSQL databases for transactional things, but Amazon, they use DynamoDB, which is a NoSQL for this complete e-commerce platform.
I said if Dynamo, yeah, right, you're right. So I said some NoSQL databases like graph databases, they are ACID. So you can use them for transactions. Like the framework that we have, Storm plus Neo4j, it is well enough for a banking transaction. So a bank can definitely use it.
Okay, sir.
RDFs?
Pardon? RDF? Okay, right. I don't have much idea about that. I need to find out. Yeah. So that's it. Okay. Thank you for listening. I know. It's a really big topic.
I know.